So hope the screen is visible. So today we are going to continue with the last portion of the ISS paper 4. We were actually doing section D, which was statistical quality control. We have completed question number 7 and as well as question number 8 till part B. We were just discussing question number 8 part. No, we have not completed question number 8 completely. 8 part A was completed and 8 part B plus 1 was done. Let me show you 8 part B1. Sorry. This was 8 part B1, which was the OC function related question, that what is the OC curve. So we have defined corresponding to that what is my inspection plan and what is my acceptance sampling. And then we have defined the OC function, and then we have defined the OC curve corresponding to any sampling inspection plan. And also we have drawn the ideal shape of an OC function, which corresponds to the 8 part B question number 1. That is, write a note on operating characteristic curve of control charts. Okay, next comes question number 8B part 2, which is EWMA, that is exponentially weighted moving average, and we need to find out its control charts and its control limits as well. So for this one, I will like to refer to this particular PDF. Here it says that exponentially weighted moving average control chart is a particular different kind of control chart. So if you can see that the name suggests that exponentially weighted and moving average. So we have learned moving average in time series, and exponentially weighted means the weight we are going to take over here is going to be a kind of some exponential weighting. So this is the weight we are actually going to take. So if you can see that this chart was introduced by Roberts and was originally called a geometric moving average chart, because obviously when the weight is exponentially moving or increasing, so basically we called it geometric moving average chart. The name was changed and then it has become EWMA chart. So this chart was like x1 x2 xn, and then we have k samples, and corresponding to this k subgroups we will have k sample means x1 x2 xk bar. Next, for this we have actually sigma, and we can replace sigma by root n. Okay, corresponding to the ith sample we can have the weight, and we can put the weight as lambda, where lambda lies between 0 and 1. Okay, so we will start with some initial value z naught, which is the first sample taken. So the first sample, let the targeted value be mu. So the first sample is mu. So we can estimate the value of this first sample mu with the grand mean, which is coming to be my x double bar. That is the mean of the all the means x1, x2, xk bar. Next, z1 will be some this kind of thing, lambda into x1 plus 1 minus lambda into z naught. Okay, so this is not lambda into some z1, this is z1 equals to lambda into x1 plus 1 minus lambda into z naught. This is actually looks like a convex combination type of things, because we know this lambda lies between 0 and 1. Again, we can like z2 is lambda into x2 into 1 minus lambda into z1, and then we can put the value of z1 from the previous step, and that is going to give me lambda into x2 plus 1 minus lambda into x1 plus 1 minus lambda square into z naught. So if you can see this lambda into x2, we are deliberately incorporating 1 minus lambda to the power 0, which is nothing but 1, to keep a parity in the writing. Then we will move on to z3, which is lambda into x3 into 1 minus lambda into x2, 1 minus lambda whole square into lambda into x1 into 1 minus lambda cube into z naught. So everything is coming in terms of x3, x2, x1. So whenever I am writing z3, So I am actually incorporating x1, x2, x3 and z naught, and the initial value of z naught was taken to be mu, and mu hat was estimated by the grand mean x double bar. So and the weights are in terms of lambda, that is 1 minus lambda to the power 0 into lambda, 1 minus lambda to the power 1 into lambda, 1 minus lambda whole square by lambda, and 1 minus lambda to the power cube, which was the suffix of z. Okay, so basically if we write z4, so that is going to be 1 minus lambda to the power 0 into lambda into x4 plus 1 minus lambda into the power 1 into lambda into x3 plus 1 minus lambda whole cube into lambda into x2 plus 1 minus lambda whole square into lambda into x1. Up to this, because this is z4, so x1, x2, x4 it's going to take, starting from the reverse order, x4, x3, x2, x1, and then what we are going to have, plus lambda 1 minus lambda whole to the power 4 into z naught, which is initially my this thing. So this is actually what we got. So in general we can write zi as lambda into summation over 1 minus lambda to the power j, running from 0 to I minus 1 x I minus j plus 1 minus lambda to the power I z naught. So we can follow the previous pattern and can write zi in general, where the initial value of z naught is given and lambda is specified to be lie within 0 and 1. So this actually is giving me my two control limits. This is my UCL, that is the mu naught plus L sigma into this. The central line is this. The lower control limit is this. Now the question is where we are actually getting this thing. We are getting this thing from sigma of Zi, that is variance of this particular big expression. If you can see, this variance of this particular extended portion will be 0, because this works as a constant. Z naught is x double bar, because we know variance of a plus b x, so a doesn't stands over here, so basically we will not get anything here. This is going to give me some lambda square into this thing, and ultimately after doing and computing all the calculations, this variance of x j I minus j is sigma square, and that is actually giving me this thing. So what is this L sigma? So this is the variance which comes under the root. So basically mu plus some 3 sigma limits we always get. But here what we are actually getting over here is mu naught plus L mu. This, what is this L mu? This L mu is specified over here. Just a minute. Yes, we will discuss the choice of L and lambda later. So this L sigma is actually a function of sigma, which is actually a variable kind of thing. So this variable kind of thing, E can specify anything. This L of sigma can be taken to be 3 as well. So then we can take on call it as a 3 sigma limit. Or if we can take it as 6, then we will call it as 6 sigma limit. So this L into sigma of this thing is basically my particular variance. So this particular portion is my variance. Square root of this thing is my sigma. So basically this portion is my standard deviation. Okay. This portion is my mean, and this choice of L is actually subjective, based on what we actually need. So this is what we have on EWMA, that is exponentially weighted moving average. And if you can see, the weights are like 1 minus lambda to the power j, that is it's going to increase exponentially, hence it is called exponentially. And why it is called moving average? Because in moving average we know that it is like xt equals to some epsilon t plus alpha into some beta naught into epsilon t plus beta 1 into epsilon t minus 1. So obviously it is a function of some x I minus j and the previous exercise, and also z naught. So basically it's the error. So that's why it is called exponentially weighted moving average control chart. Next we will move on to our next question. So this is our next question, that mention the situations where acceptance sampling is most likely to be useful. That is why we can't. This is another question, that why acceptance sampling is more useful rather than 100% of inspection. So the question can be written in another manner, that situation this is the question. So this is why the situation where acceptance sampling is useful. So what are the other way we have rather than acceptance sampling? We have the way like complete enumeration, the word we use in case of sample survey. Here we called is complete or 100% inspection. So we actually don't do this 100% inspection, and it is not at all recommended. So one thing or parallel question can be asked, that why this 100% inspection is not recommended. Okay, so basically this is what we say, that the producer may have excellent quality history, and we do not need this really 100% inspection. So based on the excellent history, of the product quality, we can avoid this 100% inspection. Number two is the most important thing, is that if the lot size is very large, if the lot size is very large, so then we can't go for 100% inspection. Third is if the inspection procedure is destructive. If the inspection procedure is destructive, means, for example, testing of firecrackers. So we can't do the 100% or complete enumeration if we are checking all the firecrackers, burning it, so we are left with zero. So we need to choose a sample, and then we need to go for this. And 100% complete enumeration is not recommended, because of one thing, that it is costly and time consuming, and also laborious. Costly, time consuming, and laborious. So, or you can write it takes the cost in terms of time, manpower as well. And last but not the least, the inspection error will be quite high for complete inspection. The inspection error. So for these reasons, we can't go for complete enumeration. Rather, we should be go for acceptance sampling. So these are the situations where the product quality has the good history. So we can go for the sample. This is the least important point. Okay, this is least important point. So you can put it at the end, and then you can cover up the whole thing. So the lot size is very large. So I am reordering the points. This is one, this is 2, and this is 3, this is 4, and make it 5. This is the least ordered, like these important point. Okay, so these, the red one, are the ordering of the actual points. Okay, so and for high inspection or the complete enumeration, the error chances will be high. So it will have, so what will be the conclusion for that? So it will actually have a high chance of being rejected. Okay, so that's why, the as a producer, the producer will not accept this thing, that his lot having a high error gets rejected, and obviously he will face a loss. So in that case, if it has a less amount of error, in if we do a acceptance kind of sampling, then obviously it will get accepted, and it will get marketed, and with a small amount of error, the consumer will be able to buy this. Okay, so this is the situations. I am just briefing the main points, so you need to write it a little bit elaborately. Next, we are moving on to our next question, that state the advantage and disadvantages of acceptance sampling. So we can actually go for the acceptance sampling for some particular reasons. Okay, so I will actually go for this particular acceptance and advantage and disadvantage of acceptance sampling later. Rather, I will like to move on to this question number 8, part C, part 3 first. Okay, so what we have just answered is 8 part C, part 1. Let me number this. Just a minute. HC1. Now we will move on to HC3. We will discuss the advantages and disadvantages later. HC3. Okay. So this is what they are asking for. The explain the operating procedure for single sampling inspection plan. Also determine the effects of N and C on the OC curve. This is a very important point rather than the previous question. That's why I am moving on to this thing. So first we need to discuss that what is this acceptance, the single sampling plan, this operating procedure of single sampling plan. So let us write this in a way of an outline. Then we can elaborate it. Okay. So single sampling plan. Okay. So description. Description is first we will introduce something. Let us write a lot of size capital N is actually taken or considered for inspection. Is, let me write, is considered for inspection. A random sample of size small n is drawn from the lot. So the total lot is capital N, and the sample of size small n is actually drawn from the lot. Okay, so all the items in the sample are inspected. So all the items in the sample, not of the whole lot. All the items in the sample, okay, in the samples are inspected, and let D be the number of non-conforming items found in the sample. Suppose small c is the maximum allowable number of sample of size n. C is known as sampling number. Okay. Now we are coming for the actual procedure. This is the description. So the procedure says if D is less than equals to C, the lot is accepted with D non-conforming items replaced by standard ones. However, if D is greater than C, the lot is rectified. Okay. So actually, if D is less than C, the lot is accepted, and this is the procedure. And the main thing is that this N and C are the plan parameters. Okay. So this is the procedure. Now we can draw a flow chart of this thing actually. What will be the flow chart of this particular thing? So basically this N comes, and so we can draw a flow chart like this. From capital N item, a small item of random sample has been chosen. So then it has been inspected. So two cases may arise if D is less than equals to C and D is greater than C. If this happens, then accepted with D items, or rather I should write D non-conforming items, replaced by standard ones, or here it is rectified. Okay. So what is actually not known to us? The two things is not known to us is this small n and the small c, and hence these two are called the plan parameters. Okay, so we need to determine this thing. The actual lot size, that is how many things we are producing, that is actually known to me. From this, we are taking a random sample of size small n. Fine. So, what will be the optimum size of the sample? That is also one thing we need to determine. And what will be this C? C actually looks like a cutoff type of things, where C is known as sampling number. So, we have written this already, still I am writing. C is my sampling number, which works as a cutoff. Cutoff means like with a lot of size this, how many defectives I can allow. Okay, so like suppose out of lot of size 100, I can allow only 2% of defects. So this is the allowable limit of this particular lot. So if that limit is equals to 2% or less than equals to 2%, so we are going to accept this lot, and we are going to replace that 2% or less than 2% items with standard or proper quality items, so that actually lot will be ready for marketed. If the number of defective items is greater than C, that is the cutoff, then actually we can't take this risk of replacing those defective ones with standard ones. Rather, we will reject the lot, and not completely reject a lot. We will actually say that this lot can go back for our rectification. We are not rejecting it directly, we are sending it for our rectification or for a correction. So this is how my single sampling inspection plan works. And for single sampling inspection plan, actually it doesn't like have a second chance of being what do I say, is being having another chance of being inspected. So this is what we say for single sampling inspection plan. So in this context, now we can go back to my previous question, where it says the advantages and sorry, no, the second part, also determine the effect of N and C of OC curve. So the effect of N and C on OC curve, how it works basically. So N and C of OC curve, it says that how it is going to determine that the function LP. Okay, so we actually have the two approaches for that. Okay, so we have two approaches. First one is LTPD approach. What is this LTPD approach? This LTPD approach is basically we are actually using this PT, LTPD, that term PT is as the consumer's risk beta. We are all aware of these two terms. Still, I am telling you, we define the consumer's risk as beta, and this LTPD as lot tolerance percent defective. Okay, what is this LTPD? This LTPD is consumers risk. Okay, so this is how we actually see this LTPD approach. And now we are going to find the OC curve, which is my LP, or OC function rather I should say. So this LP is basically probability that D is less than equals to C, that it is accepted. Okay, and non-conforming one is replaced by the conforming ones. So that is summation over D running from 0 to C, NP by D, N minus NP in D, that is combination of this, divided by NCN. So this is looks like a hypergeometric distribution, and we say that given the LTPD, that is the lot tolerance percent defective, as PT, and consumers risk as beta. Okay, so this is a hypergeometric, so we define it as HP of n and c, the function of n and c. So this pt and beta will be given. So we how we are going to find this, since this pt and beta are given, two unknowns, we will be needing two equations. We have this L of Pt is equals to H of Pt of Nc is equals to beta. This is my equation 1, and 1 is satisfied by several pairs of N and C. This equation 1 is satisfied by several pairs of N and C. Okay, so we will choose different values of N and C, and then we will be able to draw the OC function. We choose the particular pair for which the ATI is maximum. So where we are going to stop, we need a actual cutoff here as well. So we choose that particular pair for which the ATI is maximum at P equals to P bar. Okay, so basically what is my ATI is right now? This ATI is going to be my expectation of this N star, where my N star is the number of units to be inspected under a given SIP. So under the given SIP, how can I choose this N star? So we have some values of N star. One is small n, one is capital N. So two values corresponding to two values, the probability that this capital N star will take the value small n star is L of P, and one is 1 minus L of P, such that the total probability is my 1. And we will find expectation of N star. This expectation of N star is, as you can see, is going to be small n into LP plus small capital N into 1 minus LP. This thing. So this simplifies and give you capital N minus capital N into small n into LP. So expectation of N star is my, as we defined, is my ATI is equals to this I of P. So we define this I of P at P bar. So this I of P bar is N minus N minus N into L of P bar, where P bar is the process average. The pairs of N and C obtained in 1 can be used in this particular equation, naming as 2. So we can write the pairs, the pairs of N and C obtained in 1 are used in 2, and that basically what we are doing is getting a particular pair of this N and C for this from 1 to use in this particular equation 2, which we are getting later, this p bar, I of p bar, that particular pair for which this I of p bar is minimum. This is how we choose the plan parameters n and p by using LTPD approach. Next, my approach number 2 is AOQL approach. So, what is my AOQL? We know this particular term AOQL. So, AQL is basically average quality level, and OQL is basically what we say as average outgoing quality level. Okay, so this average outgoing quality level approach. So, what we are assuming over here is let Y is the outgoing quality. Okay, so AQL, which is my average quality level, is going to be the expectation of Y. So we need defined Y and this thing. So what will be the Y will take the value as? So this probability that capital Y will take the value small y. This we need to determine. This is NP minus D by capital N. D is the number of non-conforming items or 0. This is 1 minus LP and this is my LP. Total probability is 1. Okay, so expectation of Y is equals to NP minus D by capital N into L of P, which I define to be a function of P. Okay, so given that AOQL, outgoing quality level, is some PL, so let us find this. So if I do a derivative of this function and equate it with 0, and suppose we get P as P star. After equating the first derivative, we get P star, where P star is the value of P at which P is maximum. We are assuming that where P star is the value of P, where, no, not where, for which P is maximum. Okay, so what we have, this AOQL is equals to F of P star, and that is actually my NP star minus D by N into L of P star is equals to P of L. This is my 1. Okay, so this is how we get equation 1, and now we can actually find out the several pairs of N and C which satisfies 1. So we may write this particular line that 1 is satisfied we choose that particular pair for which ATI is minimum at P equals to P bar, that is I of P bar is minimum. This is how we go for the particular plan of SIP to determine N and C. Next, going for the next question, explain the operating this we have done. Next, explain the operating procedure of a double sampling inspection plan. Derive its OC curve, average sampling number, and average total inspection, that is ATI. This is a very big question. So we will go and start with explain the operating procedure of double sampling inspection plan. So this is my, I think, question number 8D. 8D says double sampling plan. Okay, this double sampling plan actually, this is basically, I am actually going to draw a flow chart, then I am going to explain. From capital N, I am taking a sample of small n1, and out of this small n1, suppose this d1 is the non-conforming items. Okay, so this d1 may give you actually three situations. What are the three situations? One situation is if my d1 is less than equals to some c1, some cutoff point c1, we accept the lot. Okay, if this d1 is greater than some c2, some other cutoff c2, we rectify the lot. But what happens if this d1 lies between this C1 and this another cut of C2? How we are going to determine C1, C2, that I am going to tell you. Then we take another sample of size N2 and we define from this N2 we have another D2 non-conforming items. Okay, so out of this D2 is giving me another two cases. What are the two cases? The two cases are actually when D1 plus D2, that is the total number of non-conforming items, is less than equals to the final cut of C2, then we accept the lot. And if D1 plus D2 is greater than this C2, we rectify the lot. So what actually is happening over here? So let me define, this is a flow chart. I am not going to write it because it contains many steps. So what this sampling plan actually deals with, it has a double step verification. That's why it's called double sampling inspection plan. The initial lot size is capital N, from which the first sample is taken as small n1, and we say that the number of non-conforming items in N1 is actually D1. So if we find that all N1 items are inspected and out of which D1 items are found to be non-conforming, then we set a cut of C1 as the number of maximum allowable non-conforming items or defective items, okay, which we can actually allow. So what actually the case should be? The case should be if D1 is less than C1. So basically we will accept the lot and we will replace those non-conforming items with standard ones. Okay. If D1 is, so this is the case 1, which is till now this is equal to the single sampling inspection plan. Now, basically C2 is the maximum allowable number of non-conforming items for a sample of size N1 and for a sample of size N2 as well. So here, since this is, if it is accepted, it's fine. So basically this is my, this actually comes under my case 1, and this both two combines and give me case 2. So under case 2 we have actually can have two sub cases. Okay, so what actually it says that first we set a cut of C1. If D1 is less than C1, we are accepting the lot, replacing the D1 non-conforming items with the standard ones. Case closed. Okay. If it is not done, then we are taking another random sample of size N2 and defining another cut of C2, which is a cutoff of which another cut of C2, which is the maximum allowable number of non-conforming items out of the random sample size of n1 plus n2. Since the random sample size is also increasing, so the cutoff will also have changed from C1 to C2. Next, we actually have two cases. What is the case? If D1 is greater than C2, we will put the lot for rectification. That is, it is not allowed. It will have need some rectification. But if this D1, that is the number of defective which was still there, lies between this C1 and C2, that is, it is greater than the allowable number of mm, uh, allowable number of non-conforming items we have set it for the first sample, but it is less than for the allowable number of non-conforming items set it for the joint sample, then we will actually go for this D2, which is the number of total non-conforming items. Then if D1 plus D2 is less than this total cut of C2, then we will accept the lot, and otherwise we will rectify the whole lot. Then in that case, we can say this N1, N2, C1, C2, these four of them are my plan parameters. This N1, N2, C1, C2 are my plan parameters. Clear?